Alright, so we're going to do more with area. So last time we did area under piecewise functions, where I had to integrate two different functions over the different pieces of the domain. So we're going to look at this case of two functions. So these are going to be two distinct functions. And we're going to find the area bounded by these two functions or in between the two functions. Alright, so this procedure is similar, but we do have to do a little tweaking with it. There are, again, because the fundamental theorem of calculus solves for area under the curve bounded by the x-axis. It's specific to the accumulation of my function values between the function and the x-axis. Well, when I have an area between two functions, that's not necessarily the case. Alright, so we do have to do a little tweaking with it. And so the theorem that we use, the area between two curves that do not intersect over a given interval, is the first one, and then we're going to look at cases where they do intersect. Alright, so to find the area between two functions, given they're both continuous, so we still have to have continuity, and we know one function is bigger than the other function over the entire, again, they never intersect, therefore, one function is bigger than the other one. I made the f of x bigger than the g of x. Then the area between the two functions can be found by a single integration and the fundamental theorem of calculus. What you have to do is you have to take the bigger function and subtract the littler function. And actually quite a unique thing is happening here. Alright, so we can solve this. We can find this is the area between f of x and g of x over the interval a to b. Right, and again, area should always come out positive. So if the answer comes out negative, more than likely what's happened is you subtracted incorrectly. Alright, so what's happening here is I've got two functions. Alright, so suppose I've got this function f of x. Alright, or g of x, we'll make that g of x. And then this function f of x. Alright, so my f of x is bigger than g of x everywhere. Alright, and I want to find the area between the two functions from a to b. Alright, so there's the area between my two functions from a to b. And so this is the area I want to find. Alright, which, like I said, we can't directly find it using the fundamental theorem of calculus. Now, I could find this area, and I'm going to show you that it does work, if I integrated my bigger function f of x and subtracted my littler function g of x over the a to b over the a to b. And I could do that. I could find my integration of two functions and subtract, and that's fine. It finds the area that way. But I can make life a little easier and use the fundamental theorem of calculus, which is the way we're going to want to use, which is this method. If I take my bigger function minus my littler function, what happens is I sort of get a new function. So I'm going to let y equal my f of x minus g of x. Alright, so I've put them together. Specifically, I've taken the big function and subtracted away the little function. And what happens is when we regraph these, where I've got my bigger function and my littler function, alright, so that would be my f of x minus g of x. That would be a to b, and I probably needed to go a little bigger here. There. That looks like that's the behavior of it. Alright, and so this is again a new function where I've taken my function f of x, g of x, and I found this area, which is now against the x-axis, and I can solve using the fundamental theorem of calculus, right? It's my x-axis. This is my function, f of x minus g of x. And as it turns out, when I want to find this area, I integrate a to b of the new function where I've subtracted and integrated this new function. These two areas, although they're a different shape, they're the same size areas. They're the same value. And when we do our first example, I'm going to go through both methods. Now, after that, we'll be using the easier one where we'll just do one integration. But technically, you could do it either way. Alright, so walking through an example where you'll actually see it with numbers. Alright, so we've got two functions, f of x and h of x over the interval negative 2 to 2. So there's my a and my b. H of x is the function negative 3 minus 3, so it's a line. F of x is the x squared minus 4. Just graph the area, shade it, and again the integration. And we're going to do it both ways. Alright, so I'm going to start off with the two functions, and so I'm going to go to my calculator, I'm going to type them in. Alright, so my negative x minus 3 is my first function, and then my x squared plus 4 is my second. Then I'm going to hit zoom standard, All right, so there's my graph. All right, there's my two functions, and so I'm going to go draw the picture. All right, so I've got my parabola that starts at 4. It's opening up. All right, that would be f of x. My line goes through -3 and has this shape, so that's h of x. And then I'm looking, oops, I think it goes a little further over than that, between 2 and -2. And so this is the area that I'm looking at. This is 2 and -2. From the x value to and -2. Alright, so that's where my functions start and stop. Alright, and this is the area I'm looking at, alright, the area under the integration. Alright, so that's my area, which again, I can solve it with two integrals. My f of x is obviously the bigger function, right? It's above my h of x everywhere. And so I could integrate from -2 to 2 of my x squared plus 4, and then subtract away integrating my smaller function, which is the -x minus 3. Alright, and so I'm going to do that. I'm going to go to my function, I'm going to graph. The biggest thing is to make sure you're on the correct function. So hit second trace 7. Make sure I'm on the littler function right now, so I want to hit my up arrow, and now I'm on my big function. Alright, so I'm going to integrate my big function from -2 to +2, and when I do, it comes out 21 1/3. Alright, so this comes out 21 1/3. Alright, and now I subtract whatever the area is under my g of x, or h of x. Alright, so second trace 7. Make sure I'm at the right, and so I am. That one I don't have to move. I'm already on my -x minus 3. Integrate from -2 to +2. And there's the area. Alright, so there's the graph that I shaded, and so that comes out -12. Alright, so 21 1/3 minus a -12 really means plus a -12, so that's 33.33 repeating, or 33 1/3. Alright, so there's my area. That area is 33 1/3. Alright, that's the method if I want to use two integrals, and that's a perfectly fine method. There's nothing wrong with that. But we do prefer the other simpler case, because again, it's kind of unique that this happened. We can find the area using one integration. So integrating from -2 to 2, x squared plus 4 minus a -x minus 3. I find that simplified, right, there's my new function where I'm going to simplify it. So integrating from -2 to 2, x squared minus x plus 7 when I simplify that, right, because it's distribute here, those become positives, and so it's just x squared plus x plus 7. Alright, and so this is the function I'm now going to find the area under. So I'm going to go back to my graph and regraph this new function, right? That's that new function where I've subtracted. And so I'm going to go back here, I'm going to clear all this out. Alright, and then I'm going to type in my new function, x squared, oops, clear, x squared plus x plus 7, graph, and so now I've got a new function, it's a new parabola. Alright, it's different, right? If you look at it, it's not on the origin anymore. I'm going to integrate it between my values, -2, +2, and it'll shade in new area, -2, +2. Alright, and so it shades in a new area, but it gives me the same value, 33 1/3, right? 33.33 repeating. And so this comes out the same thing, right? It's the same area that I found up here. But I got it using a different graph, right? Where this graphed two functions, and I had to find the area of the function above and subtract away the area of the function of the other one. This one graphed a totally new function, right? That was my new expression where it was f of x minus h of x. And I integrated from -2 to +2, and this area came out the same, 33 1/3. And so this is our preferred method. We'll do another example, and I'm going to walk through it again. The pictures, now I'm only going to solve it using this second method, although like I said, the first method is perfectly fine too. If you prefer it, if that one makes more sense to you, again, it's not wrong, it's just a different way. All right, next example. Find the area bounded by the graphs of h of x and g of x over the area 1 to 3. All right, h of x is the e function 2e to the negative x, and g of x is the expression 2 divided by x. All right, so again, first thing I'm going to do is look at the picture, right? Graph the area you want to shade, and then the integral you need to solve. All right, so the first thing I'm going to do is kind of get my picture. So I'm going to clear out what I have here. And so I'm going to type in 2 divided by x there, and then above my 2e to the negative x. I think a standard window should work, so I'm going to start with a standard window. I may, since I'm going between 1 and 3, I might zoom in over here between 1 and 3. So I might make my window a little smaller. I might just go to -5, leave the 10, and then I don't need to go down as far. So again, -2 maybe, and 5. Let's see if that gives me kind of a better looking graph. Alright, so there's my first function, there's my second function. Alright, so my first function and my second function. Alright, so if I graph it, alright, so x divided by 2 is the one that's up here, right? That's the one that's the butterfly-like shape. And then the e function's below that. So the e function's coming down and approaching the line pretty fast. And again, I have it slightly above it, but it approaches pretty close. Alright, and we want to find the area from 1 to 3. Between 1 and 3. Alright, so this is the area that we're looking for. We want to find the area between these two functions, between 1 and 3. So this is my g of x, alright, 2 over x, and this is my h of x, which was my 2e to the negative x. Alright, now like I said, you could, if you wanted to, integrate the two pieces and subtract. I'm not. I'm going to write out my function. So 1 to 3 is what we're looking for. My bigger function's the g of x, the 2 divided by x. My smaller function over the part that I'm looking at is the 2e to the negative x. All right, there's really nothing to simplify there, and so that's the one I'm going to solve and find the area. All right, so I'm going to go back to my graph, and I'm going to clear that one out, and I'm going to go to my second function here, and then I'm going to subtract the e term from it. So minus e to the negative x graph, and so I've graphed a new function. All right, this is an entirely new function, and I'm going to integrate it from 1 to 3. So second trace, integrate it from 1 to 3. There we go. Integrated from 1 to 3, and so the area is 1.879. All right, and that's the area that we found, 1.879. All right, where we only have to do one integration. This is the function I have to type into my calculator and integrate. Oh, I forgot my 2. I was like, my number didn't seem to come out right. I forgot my 2, so I'm just going to change it here. 2 e to the negative x. And I gotta delete that x. 2 divided by x minus 2 e to the negative x. Graph. Alright, so similar looking picture, except my answer should come out a little bit smaller. 7 from 1 to 3. That looks more right. Alright, that's more like what I got earlier. So 1.56 is the right area. Alright, 1.56. Make sure you write the right answer. It's 1.56 once I get the right thing typed in there. Alright, so that finishes up the area between two functions where they're never intersecting. One function's always bigger than the other function. Alright, and again, we can use one integral or two integrals. Like I said, you can use either method you want. Both of these methods are perfectly fine. Use whichever one, again, you prefer. This is the one that, like I said, we prefer. All right, but it doesn't mean that's the way you have to solve it. You could use the first method. Again, both of them are fine. All right, the next example is going to be basically more of this, except we're going to add step to it. We're going to find the area completely enclosed by two graphs. And so there'll be an additional step where they intersect twice. Right, that's the next set of notes.